Hello everyone. My name is Chen, and come from Shanghai Astronomical Observatory. And Dr. Shuli So is also come here to attend this meeting. The title of my presentation is Early Updated GNSS Orbit and Clock Correction. My presentation includes 4 parts. The first, I want to introduce the background. As a whole, the performance of the global navigation satellite system is improving, and the early updated orbit and clock of GNSS will be used by most users because of the timeliness and the high accuracy. The portable breakdown satellites or stations can be found earlier, and the productions with better accuracy are the advantage for the early updated orbital and the clock. The early updated BDS, Galileo, GPS, and GLONASS orbit and the clock have been produced routinely in Shanghai Astronomical Observatory, namely SHAO, at center of the ATMOS. These figures shows These figures shows the productions of Shanghai AC, include orbit and clock, aerosphere, ROTI, ZTD, ERP, IFB, DCB, ISB, and some quality parameters. The accuracy of the 6 hourly update and 1 hourly update orbit and clock productions was analyzed in this study. The second part, I want to introduce the method and the strategy of our software. The software package was developed based on the Panda software provided by Dr. Mao Ge at GFZ. And these figures shows is the flowchart, and this one is some descriptions. First, we collect some data from IGS, MGS, and say PY01 in China, and ATMOS stations. Second, we do some pre-process, and then do quality control, and then POD, and then do some assessment, and then we generate the productions. And this tables shows us the observation models and force models used in my POD. And this figure shows the geographic distributions of the stations used for BDS, Galileo, GPS, and the GLONASS. The red colors represent the IGS stations, and the blue colors means the MGS stations. And the green color is say MOLC stations. Say MOLC means across the observation, across the movement observation network of China, and the yellow one represents the ATMOS stations. And these two figures shows the mean number of the stations used in our POD, and the 6H. The 6H represents 6 hourly updated GNSS productions, while hourly updated GNSS productions are marked by 1H. We can see from the figures the hourly observation data is collected in my study, and the time span is from 60 to 90 in the year in this year. Yeah. And this table shows the mean set numbers used in POD for 6H and 1H, usually more than 100 sets. And this figure shows the slide window. The slide window is 6 hours for 6 hourly updated GNSS opto and clock productions, and 1 hour slide window is for hourly productions. There is 24-hour observation session and 24-hour practical session included in opto and clock productions. The practical opto is calculated by 2-day opto fit, and the practical clock is computed by modified ARIMA method. And the third part is analysis of hourly updated GNSS orbit and clock. And we found some reference productions, namely for BDS orbit and clock are compared with GPM productions from GFZAC. And the reference orbit and clock of Galileo is COM productions from Code AC. GPS productions are compared with IGS fellow productions. The reference orbit of Galileo GLONASS is IGL from IGS fellow productions, while the reference clock of GLONASS is from SIC. The RMS and STD of PDS, Galileo, GPS, and GLONASS, 1H and 6H clocks are shown in the following figures. We can see that in the figures there are include observation session and practical session. This is observation session, and this is practical session from the first hour to 6th hour. And there are 1H RMS and STD, and 6H RMS and STD are shown in the figures. And this figure is showing BDS GO, and this is for BDS IGSO MEO, and this figure is for Galileo. And this figure is for GPS, and this is for GLONASS. We can see from these figures there is not much difference between the mean RMS and ST of 1H and 6H for the observation session. And the RMS of 6H clock practical session is increasing from the 1st to 6th hour, but the STD is not changing larger. The RMS and the STD of practical session for 1H clock are relatively stable. The observers improvement from 0.9 nanosecond to 1.1 nanosecond is found for the accuracy of the 1H clock relative to those from 6H. And we can also see the accuracy of BDS-GO worse than BDS IGSO MEO, which may be affected by low enough size and poor satellite constellation. The RMS of 1H and 6H GNSS orbit is shown in these figures. We can see also in these figures also the observation session and the practical session. And this is for BDS-GO and BDS IGSO and MEO for Galileo, GPS, and GLONASS. We can see from these figures the RMS of observation session for 1H and 6H orbit is approximately at the same size. The RMS of 6H practical orbit is increasing from the 1st to 6th hour practical session, while the RMS of 1H practical orbit is relatively stable and shows an improvement accuracy from 0.2 centimeters to 4.3 centimeters relative to 6H. At last, there are some conclusions and summary. In general, the accuracy and precise of the hourly clock and orbit production are nearly equal to 6-hourly updated productions, which can be used by users who need real-time and high accuracy clock and opt. The average of obvious improvements from 0.1 nanosecond to 1.1 nanosecond can be found on the accuracy of the hourly updated clock than those from 6-hourly updated. For BDS and Galileo at present stage, the hourly updated orbit and clock predicted productions are more accuracy for users than 6-hourly updated. On the other hand, the portable breakdown or unhealthy satellites or stations can be found earlier is the obvious advantage for hourly updated productions. More stations should be included, and the strategy and algorithm should be improved in the future work for getting better accuracy and precise productions. Thanks.